Imagine a game, a simple one at that. You pick any whole number, it doesn't matter if it's big or small. This is where the fun begins. If the number is even, simply divide it by 2. Easy, right? Now if you land on an odd number, things get a bit more interesting. You multiply it by 3 and add 1. That's it, those are the only 2 rules. This seemingly straightforward game is the crux of the Collatz Conjecture, a mathematical puzzle that has stumped mathematicians for almost a century. The conjecture proposes that no matter what number you start with, repeatedly applying these 2 rules will always eventually lead you to the number 1. It's like a mathematical funnel, with every number eventually swirling down to that magic number. Despite its deceptive simplicity, the Collatz Conjecture remains stubbornly unresolved. Mathematicians have tested it on countless numbers, from the smallest to the astronomically large, and the conjecture has held true every single time. Yet a definitive proof, a mathematical guarantee that it works for all numbers, still eludes us. This is the allure of the Collatz Conjecture. It's a tantalizing puzzle that seems so simple yet has proven to be remarkably complex to solve. It's a testament to the fact that even in the world of numbers, mysteries abound, waiting to be unraveled. Let's delve a little deeper into the heart of this captivating mathematical puzzle. The Collatz Conjecture, named after the German mathematician Lothar Collatz, revolves around a specific function, often called the 3n+1 function, or the hailstone sequence. The rule of the game, as we've established, is simple. You start with a positive integer, any positive integer. Let's call this number n. Now here's how the function works. If n is even, divide n by 2. This gives us an over 2. If n is odd, multiply n by 3 and add 1. This gives us 3n plus 1. That's it. Those are the only 2 operations you perform. Now you take the result of your calculation, whether it's an over 2 or 3n plus 1, and you apply the same rules again, and again, and again. You keep repeating this process, and something fascinating happens. The conjecture states that no matter what number you start with, this iterative process will eventually lead you to the number 1. It's like a mathematical dance, with the numbers bouncing up and down, seemingly at random, but always ultimately finding their way to the same destination. Let's take a closer look at what happens when we apply the Collatz function to odd numbers, as this is where things get particularly interesting. When you encounter an odd number, the rule dictates that you multiply it by 3 and add 1. This operation, 3n plus 1, always results in an even number. Think about it. When you multiply any odd number by 3, the result is always odd. Adding 1 to an odd number always makes it even. This seemingly simple observation has profound implications for the behavior of the Collatz sequence. It means that every time we encounter an odd number in our sequence, the very next step is guaranteed to be a division by 2. The odd number, after being transformed into an even number, is immediately cut down to size. This suggests a kind of balancing act at play within the Collatz Conjecture. Section 4. The balancing act of even numbers. While odd numbers in the Collatz sequence experience a temporary growth spurt when they are multiplied by 3 and increased by 1, even numbers provide the counterbalance. Every time we encounter an even number, we simply divide it by 2. This halving operation is crucial because it consistently shrinks the numbers in our sequence. As we continue to apply the Collatz rules, this interplay between the expansion of odd numbers and the contraction of even numbers creates a fascinating dynamic. It's like a seesaw, constantly in motion, with odd numbers pushing the sequence upwards and even numbers pulling it back down. The conjecture hinges on the belief that the downward pull of the even numbers will always, eventually, win out, guiding the sequence towards the ultimate resting point of 1. Section 5. Why cycles are a dead end. One of the intriguing aspects of the Collatz conjecture is the apparent absence of any cycles other than the trivial cycle 4, 2, 1. A cycle in this context would be a sequence of numbers that repeats indefinitely, never reaching the number 1. While it might seem intuitive that such cycles could exist, mathematicians have used a clever tool to demonstrate why they are improbable modular arithmetic. Modular arithmetic, in simple terms, is like a clock. Just like a clock wraps around after 12, modular arithmetic deals with remainders after division. For example, in modulo 4 arithmetic, we only care about the remainders when a number is divided by 4, so 5 is equivalent to 1, because both leave a remainder of 1 when divided by 4, 6 is equivalent to 2, and so on. When we analyze the Collatz function using modulo 4 arithmetic, we discover that numbers belonging to different remainder classes, 0, 1, 2, 3, tend to transition to other specific classes. This analysis reveals that cycles, other than the 4, 2, 1 loop, are highly unlikely because the transitions between these remainder classes don't allow for closed loops. Section 6. The evidence so far. Despite the lack of a complete proof, mathematicians haven't been just twiddling their thumbs. They've amassed compelling evidence supporting the Collatz conjecture. Supercomputers have tirelessly crunched numbers, testing the conjecture on an astronomical scale. The current record stands at 2 to the power of 90, a mind-bogglingly large number, and every single number tested so far has eventually cascaded down to 1. While this doesn't constitute a mathematical proof, it's a powerful testament to the conjecture's robustness. Furthermore, mathematicians have explored various approaches and made significant progress in understanding the conjecture's intricate behavior. While the final puzzle piece remains elusive, each new insight, each new theorem proven, brings us closer to unraveling the mystery. Section 7. The quest for a concrete proof. The beauty of the Collatz conjecture lies not only in its simplicity, but also in its enduring resistance to a complete and utter proof. It stands as a tantalizing challenge, a siren song for mathematicians, beckoning them to unlock its secrets. The absence of a proof doesn't diminish the significance of the problem. In fact, it amplifies it. The pursuit of mathematical proof is a journey of discovery, pushing the boundaries of our understanding and often leading to unexpected breakthroughs in other areas of mathematics. So, the next time you have a few moments to spare, pick a number, any number, and embark on your own Collatz adventure. See for yourself how this deceptively simple rule unfolds, leading you on a captivating numerical journey that always seems to end at the familiar doorstep of 1. Who knows, you might even stumble upon that missing piece, that spark of insight that finally cracks the code of the Collatz conjecture. The challenge awaits.